Welcome engineering statics students. This is ENGR ampersand 214 at Bellingham Technical College. The topic of this lecture is force system equipollence. That's a big word to mean effectively equivalence. So sometimes you need to replace a group of forces and couples with something simpler, or you need to replace one single applied force and or force and couple with a whole bunch of other things. But you need those two different systems to have the same effect on the body you care about. So maybe you have a bracket and a rope that you're using to stabilize some suspended load in place, and you don't have the right crane, so you need to replace that with maybe a man lift and a side stabilizer or something. So you need to know how much force and moment needs to be applied with a different system to get the same thing that you did with the first one. So that's the idea of equipollence or equivalence of a force system. The technical definition that we're going to use to springboard to make some mathematical equations that we can use to do this in practice is equipollent systems are systems of forces which result in the same net force and moment. So the sum of the forces and the sum of the moments from system 1 is going to be the same as system 2. So we can write that down here with math. The sum of the forces in force system A equals the sum of the forces in force system B. So this is direction and magnitude. And the sum of the moments in force system A is the same as the moments in force system B. So in this case, A and B refer to a force system. And forces could include couples, so anything that can apply a force or a moment. Okay, let's give an example to kind of show how this would work in practice. So we have this bracket that's kind of sitting up against a wall, and initially it's being held up and in equilibrium somehow against whatever forces are applied by the wall by F1 applied at point A. And somebody says, you know, we can't keep applying a force with this point at A to keep this bracket up, but we can attach a force applied vertically up here at the wall at B, and we can apply a couple of horizontal forces out here at these corners at D and E. And we can apply them in any direction. You just tell us what you want. So, but you got to take away F1, and you can add an F4, F3, and an F2 with whatever direction and magnitude you want. What do you tell them to use for directions and magnitudes of F2, 3, and 4 to have the same effect F1 did? Now, chances are F1 was keeping this thing in static equilibrium, not accelerating up or down or twisting around. So that's likely what was wanted, but generally speaking, you're just being asked to match it here. So how do you go about doing that? Well, we start by saying, what the heck was F1 doing in the first place? And to do that, we need to take a point of action to start calculating our moments, because as you recall from our chapter on moments, when we're looking at the action of an applied force, not a couple, the point that you take the moments about matters. So we need a reference point to collect our moments, such that when we start assigning magnitudes to these forces, we can look at the moment that they would have about the same point. So that's, you gotta calculate moments about the same point if you're going to look for force equipollence, is it having the same effect. And then we can just look at the direction, and of course we can sum the forces of F1 is just one force, so it's an easy sum. So step 1, we're going to find the sum of the forces and the sum of the moments about a reference point. I picked B. You could have picked any other point. B is kind of easy, as you'll see further on. There's a way to make your life easy by picking the right points, but it doesn't matter. The worst is you do another bit of math. Okay, for F acting at point A. So F is acting at point A. We're going to calculate the moment about B. Pretty easy. So we can look at just at the action of F1. The sum of the forces in the vertical is 250 pounds upwards. There are no forces in the horizontal because F1 is the only force we have and it's pointing straight up. And the sum of the moments about B is simply the moment due to F1, acting at A. So we can use our simplified definition of moment and say that we know that F1 is pointing vertically, and we know that its line of action is going to be offset 4 feet from point B, perpendicular. So we don't have to do a cross product. We know it's perpendicular, and we got that from looking at these dimensions here. We know that from B to D is 10 feet, and D and E are in a vertical line. You can assume that. It may not look like it from the figure, but they are. And so you can say that by difference, point A is 4 feet from a vertical line that would pass through B. So the moment about B is 250 pounds times 4 feet, and this is going to be directed into the paper by the right-hand rule. So remember, we draw a radius, the radius first. So the radius from B to the line of force, and then the direction of the force. So the right-hand rule would be curling our fingers around with our thumb into the paper. And so that gives us a 1,000 foot-pounds into the paper. So the sum force of F2, F3, and F4 has to all sum up to 250 pounds vertical, non-horizontal, and the net action of all of these three forces is going to have to produce a moment around B that's equal to 1,000 foot-pounds directed into the paper. Now there could be a whole lot of answers to that, except our life is made simple by the fact that F1 is vertical, and there's no horizontal in our first force system. And that means that F2 is going to be the only net force that we have in our system, so it's the only one oriented vertically. So F2 by definition is going to have to be 250 pounds. F3 and F4, we don't know what the magnitude is, but we know they got to be equal because we know that the forces in the horizontal have to cancel out to be equipollent. So we have F2, and we know that F3 and F4 are the same. So a way to say that mathematically is F3 equals F4, and F3 and F4 are the only forces in our new system that can create a moment about point B. F2, the line of F2 passes straight through B, so it doesn't contribute to the moment in the new system at all. So our 1,000 foot-pounds into the paper has to come from F3 and F4. So, and they're the same value. So F3 and F4 are actually a couple. So we could make our life easy and almost do a head calculation. They're separated by 10 feet, and we could apply our couple formula of the force times the distance in between, and get 100 pounds for each of those. And then we would just need to know that they would have to be oriented opposite the way that they're shown to direct that into the paper rather than out of it. So that is an example of how we would get an equipollent system. We matched moments about the same point. We matched the sum of the forces in the vertical and in the horizontal in both systems, and that gave us enough equations to solve for everything we needed to know. So that is it for a real quick discussion on equipollent systems. We're going to continue this same discussion, bits of it, all the way through the course with respect to equations of equilibrium, because we started to use that. Summing forces, summing moments. If we're going to keep something in static equilibrium, we're going to sum those to 0 and solve for what we need, any unknowns we have. But if we're talking about an equipollent system, the results of those sums is going to have to be the same for one system to the other. And that is it for this lecture.